When we talk about a compound, often will want to talk about how well it will dissolve in a given solvent or its solubility. And quantitatively, we talk about its solubility in terms of the amount of solute that can be dissolved in 100 grams of water at any given temperature. Now, we've talked theoretically about whether a compound will dissolve, and we've talked about it in terms of qualitative solubility, but quantitatively, we haven't looked at how much of a solute will dissolve in a solvent. Now, we use 100 grams of water, but we also know that water has a density of 1 gram per milliliter. So 100 grams of water also has a volume of 100 milliliters. Now, when we're looking at the solubility of any solute in water, we have two factors that can affect it. For solids, the main factor affecting its solubility is the temperature of the water. So if a compound will dissolve in water, when we want to look at how much will dissolve, the temperature of water influences that. When we look at a gas, not only does temperature affect how much of a gas could dissolve in water, but also the pressure that it's under. And we understand the pressure intuitively because if we've ever opened a can of pop or a bottle of pop and we have the gas come out when we open it. Now, solutions can be described as either being one of three cases, depending on how much solute is dissolved in. So a saturated solution that contains the maximum amount of solute that could dissolve in 100 milliliters of water, or any other solvent for that case, at a specific temperature. A unsaturated solution has below the maximum amount, and a supersaturated has above the maximum amount. And you might be wondering, how do we get above the maximum amount at a given temperature? Well, if you've ever seen a sugar slurry, that explains it. But what we could do is I could heat up some water to a temperature, dissolve the maximum amount for that temperature, and then allow it to gently cool. And rather than having some of the solid precipitate out, it can stay suspended in solution. It's not necessarily a stable solution, because if I were to whack the side of the container, I could cause a precipitate and bring it down to a saturated solution. Now, when we look at temperature, we can have a variety of different things. Okay, solids generally have a higher solubility at higher temperatures. Okay, well, this makes sense because we talk about whether or not something dissolves in terms of the attractions between the particle of the solvent and the particles of the solute. And so if we're talking about water, for example, water has really high attractions between itself, but if we heat up that water a little bit, it makes it easier to break the attractions between the water molecules and therefore let it form attractions between the solute particles at a greater amount. Okay, gases, however, solubility is the opposite in temperature. Okay, generally gases have a higher solubility at a lower temperature than a higher temperature. Okay, and then finally, when we look at the solubility of liquids, so for example, ethanol in water, there's not as great a trend in terms of temperature as there is for solids and gases. So as a result, what we could do is we could look at the solubility of any given compound versus the temperature of the water. And so if I were therefore to take sugar and determine the maximum amount or the maximum mass of sugar that would dissolve in any given temperature of water, I could then plot my results in a curve. And so for example, at 40 degrees Celsius, I could dissolve about 240 grams of sugar in 100 mils of water. At 80 degrees Celsius, I could dissolve about 360 grams of sugar in 100 mils of water. And so this, therefore, would represent my saturation point. And this is my saturation point for any given temperature. So this is a maximum amount that will dissolve at that temperature. The reason we stop at 100 is because this is the temperature at which water becomes a gas. We don't go below 0 because water is a solid. Okay, now if I have a situation where I have a greater amount than this line, so for example, if I had a solution at 40 degrees Celsius, but I had about 425 grams of sugar dissolved in 100 mils of water, we would describe that solution as a supersaturated solution. Likewise, if I was below, so if at 4 degrees Celsius, I only had 175 grams of sugar dissolved in 100 mils of water, then that would be an unsaturated solution. So this line provides my saturation. Above it is a supersaturated solution, below it is an unsaturated solution. So we can see here that sugar is really affected by temperature. Salt is not. So this would be sodium chloride. It's not as affected by temperature. So as a result of this, we could determine a number of different things. One of the things that we could determine is how much of a compound we would have to dissolve to get to a saturated solution at a given temperature. So we have a curve here. So this is similar to the last one, except now rather than having only one compound, we have multiple. And so we're looking for potassium chloride. So just like we always do, we first write down our given. So we were told the volume of water. Yes, we were given a mass of water, but remember the density of water is 1 gram per milliliter. So 100 grams has a volume of 100 milliliters. We have our temperature of our water. So now what I can do is I can go to my graph and I'm going to read up until I hit my potassium chloride. And then I can read across, and this will tell me my saturation point, or the concentration of a saturated solution. And so therefore, from my graph, I can get that a saturated solution has 45 grams of potassium chloride per 100 milliliters. So now I know that concentration is equal to mass over volume. So therefore, my mass would be equal to concentration times volume. So now that I have my equation, I can substitute in my values, and I would get that I would have to dissolve 45 grams of potassium chloride into 100 mils of water at 60 degrees Celsius to get a saturated solution. More interestingly, and more interesting question would be, how many grams would I expect to crystallize out if I cooled a solution from a higher temperature to a lower temperature? Well, we have our curve. Just like we always do, our next step is to write out our givens. So we know the volume of our solution, we're told it. We know our two temperatures. Okay, so now next what I would do is I would go to my graph and I would read on the graph the solubility or concentration of a saturated solution at 80 degrees Celsius. So I would go up till I hit the curve and go across. And I would see my saturation point. So at 80 degrees Celsius, the saturated solution has 22 grams per 100 milliliters. And then at 20 degrees Celsius, I would also go up. And I have a solution around 10 grams per milliliter. Okay, and then after that, I could then determine the mass of potassium sulfate in each of these solutions, right? So my mass at 80 degrees Celsius would be equal to the concentration times the volume. So my 250 mils of water has 55 grams of potassium sulfate at 80 degrees Celsius. Then I can do it at 20, and it would have only 25 grams. So now what I can do is the difference between these two masses is the difference in the maximum amount that it could hold. And so therefore, that's what I would expect to crystallize out. So their difference in their mass would tell me the amount that I would expect to crystallize out. Now, if I were to look at the effects of pressure for gases, what we find is that since pressure is defined as the force per unit area, the higher pressure, the greater force I have pushing my gas into solution. So therefore, a pressure, but also because solids and liquids have a defined volume, pressure doesn't impact them as much. Whereas gases, since they have so much space between the particles and pressure can push them together, pressure impacts the solubility of gases really highly. And so therefore, as I increase my pressure, I can increase my solubility. right? Because I can push more particles in to the solution. And so that's higher pressure has higher solubility of a gas. And we understand this intuitively, again, because if we open a carbonated beverage and we have the gas come out, we decrease the pressure of the system and allow some of the gas to come out of the solution.